Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The problem of classifying topological spaces up to homeomorphism is extremely difficult. And part of the reason why that is so is because there are very similar topological spaces that algebraic invariants cannot distinguish. What I want to do in this video is to introduce the notion of homotopy, which allows you to weaken the notion of homeomorphism to that of homotopy equivalence, and so address this problem and say more precisely what algebraic invariants can do to study topology. Okay, so let's look at the notion of homotopy. And the basic idea of what we want to do here is we want to reduce, in some sense, the number of maps that are involved by identifying certain continuous maps which are deformations of each other. So let's go to the definition here. So the situation we consider here is we'll have two continuous maps, f0, f1, both with the same domain and codomain, so say both from x to y. And so a picture to keep in mind would be, suppose for example x here is this circle, and y is just this board here, and then we can map this circle, for example, here, like this, or we could also map it over here via f1 to this bigger loop around like that. Okay, so what is a homotopy from f0 to f1? So the way we should think about it is that we want to deform this map from this first one, f0, to this one here. And one way to think about this is you can think of this as a map from this circle to the whiteboard, and you can slowly over time deform it by growing this loop from the small one, f0, to the one that gives you f1. Okay, so that's the basic idea of what you want to do. And that process of slowly growing from f0 to f1, that deformation is called a homotopy. So what's the mathematical definition of this homotopy? Okay, so what we want is we're going to have a map from x cross the unit interval 0, 1 to y. And what happens is that the elements of this unit interval you should think of as a time parameter. Okay, so this is a continuous map from h cross 0, 1 to y, and it has to satisfy certain properties which relate it to the two maps f0 and f1. The first point is that time t equals 0, so when you restrict it to the value where the second coordinate is 0, and you look at h, so this is now a map from x to y, you just recover f0. And when you look at what h is at time t equals 1, okay, so when the second coordinate is 1, this is a map from x to y again, and that just gives you f1. And that's the definition of a homotopy from this continuous map f0 to f1. As usual, there's some natural notation and terminology that comes with that. We say f0 and f1 are homotopic in this case, and the notation here perhaps is not completely standard, but it's fairly common. Sometimes it's good to say that you have a notation for h as a homotopy from f0 to f1, so I'll use this notation here, h from f0 tilde f1. And the other thing is that, well, what you might want to do, remember you're thinking of this as something that grows. It's a map at time 0, it gives you f0, and then grows up to f1. So at any particular time, maybe it might be like this. That's what it is at time t. And it makes sense to talk about the deformation at time t. What you do is you just look for t inside this unit interval. Okay, you can just fix that value and look at the corresponding map from x to y, and that's what it is at time t. Okay, so at time t equals 0, you just get the first map, and as you increase t from 0 to 1, eventually you'll get the second map, and that's the homotopy. A little bit more terminology that's associated to what might happen. Sometimes we want this homotopy to fix a certain subset S of X. So suppose, for example, you have a point here, and suppose f0 maps this point here to this one here, and f1 also maps this point here to this one here. Well, maybe you want in this homotopy, as you're deforming this loop, that at all times, okay, this point always gets mapped to there, so it's fixed in time. Well, in that case, we'll say that h fixes that point, or more generally, it can fix a subset. Okay, if for each point s inside this subset, you look at this hs and you look in all time, this map is constant with respect to time. It doesn't move as you go from time t equals 0 to t equals 1. Okay, so part of the reason why we introduce this is that often we want to look not at topological spaces, but what are pointed spaces. And that just means a pair consisting of a topological space like X and some distinguished point x0 that you've picked. Okay, so if you've got a continuous map of pointed spaces, okay, so suppose you have two of them, F0 and F1, okay, so that just means continuous maps from X to Y, such that both of them, Fi, will send the distinguished point here, x0 to y0, okay, then you could talk about homotopies between these two maps as well as maps of pointed spaces. And it just means a homotopy of F0 and F1 as continuous maps from X to Y, which fix the distinguished point x0. So all of these FTs will also be continuous maps of pointed spaces. Okay, so that's a setting that will often be useful in topology. Okay, so we've now introduced this notion of homotopy. What are some basic facts about this? So the first thing is that this is actually an equivalence relation. Okay, so we're looking at continuous maps from X to Y. You can look at the set of all continuous maps from X to Y, and then this is a relation to say that F0 is homotopic to F1, okay, when there exists such a continuous map, and I claim that this relation on the set of continuous maps from X to Y is an equivalence relation. Okay. The most important consequence of this is that actually now we can talk about a homotopy category, and I've used this notation here, homot, with an underline here to denote this. So this is a way of studying topological spaces, which is not as refined as looking at things up to homeomorphism. Okay, so what do I mean by that? Okay, so firstly, what is it? So it's a category, so it has objects and it has morphisms. So objects are just topological spaces again. That's the first thing. And the second thing is that what are the morphisms? The morphisms now are not just continuous maps, they're going to be homotopy equivalence classes of continuous maps. Okay, so that means that we're identifying all those continuous maps which are, in a sense, continuous deformations of each other. Okay, so you've lost some information when you go to this. Okay, and a part of the reason why we want to introduce this is that when you look at algebraic invariants, okay, it can't distinguish a lot of things, and some of the information that is lost are things where you have homotopic maps. Okay, so there are two very, very important facts. I've stated them in the context of topological spaces, but you can also state them, and it's true, in the context of pointed spaces as well. And that's something that will be used in future. Okay, so let's just see roughly why it's true, and I don't want to go through the proofs in detail. Sometimes it's best to just think geometrically about what's going on. Okay, so I claim that tilde is an equivalence relation. Okay, so for example, the best way to think about this is to think in terms of deformations for your idea of what is homotopic. If F0 is homotopic to F1, let's check symmetry. That means you can kind of deform it by growing this up to F1. And of course, you can run this backwards and then just shrink F1 back to F0. Okay, so basically, if you swap, if you apply a reflection about half for this interval, that means that you essentially, the map you'll get here will be running this map backwards, and that gives you a homotopy from F1 to F0 instead of F0 to F1. Similarly, if you grow F0 to F1 and then F1 to some F2, then going twice the speed, you can grow all the way from F0 to F2. And that gives you transitivity of this equivalence relation. And it's pretty easy to see that, that if these two are the same, then you can make all of these F's 0 up to F1, all these FTs constant. Okay, F0 equals F1, so you make them all equal to FT. Okay, so basically, this homotopy H fixes all of X, and that will give you the homotopy from some function F to itself. Okay, so that's why it's an equivalence relation. So the more interesting thing is how do you get a category out of this? So I told you the objects and the morphisms. Okay, so identity, I hope you can guess, is just the identity, the equivalence class, homotopy equivalence class of the identity continuous map. So the more interesting thing is how do you define a composite of these equivalence classes. And there's a kind of natural definition that's associated with this. So let's have a look and see what it is. So suppose now you have continuous maps x and y, x to y, let's say given by f or g, okay, and a continuous map from y to z. Okay, so of course here what you want to do is you want to say, well, let's look at the homotopy equivalence class of H, and you need to compose that with the homotopy equivalence class of F. And the thing that you'd like to say is that to make the definition that you would want here is that you want to make this the homotopy equivalence class of just a composite H composed with F. Okay, that's what you would like. But for this to be true, that means that suppose I change the representative element F here to something homotopic, which is G. So suppose H is a homotopy from F to G. Then what we'll need is that this homotopy equivalence class doesn't change when you replace F with G. In other words, H composed with F is homotopy to H composed with G. So they're the types of things that you'll need to check if you want to make this definition, and this is the definition of the composite of morphisms here. That's the thing that you need to check. So let's just see, why is H composed with F homotopic to H composed with G? So remember, these are both maps from X to Z. So we need a homotopy like this, but where you go from X cross 0, 1 all the way down to Z. And what is that homotopy? So firstly what we'll do is we'll use the homotopy we're given between F and G, which goes from H, which is H from here to here. So we use that first. And then now we've landed in Y, and we're going to apply H to that. That's the natural thing to do. So we'll apply H to that. And we need to check that this is a homotopy. So what are the things that we need to check? The first thing, it's a continuous map from, in this case here, so you've got maps from X to Z. So you want a continuous map from X cross the unit interval to Z. And we've certainly got that because this is a composite of continuous maps, and the codomain and domain are correct. And then you have to check that at time t equals 0, it gives you the first one, and time t equals 1, it gives you the second one. Okay, so let's check what's going on at those time. Okay, so let's look at H, and you're going to evaluate at some x at time 0, and you want to apply H0 of that. Okay, H0. So what's this? Well, this is a homotopy from F to G, so at time 0, this is just f of x. So you have recovered just this first one here. And a similar argument shows that if you replace 0 with 1, then you'll get this here, gives you H composed with G. So that tells you that indeed this is well defined when you change this F to something homotopic. Simply you have to do a check that's like this, where you replace H with something that's homotopic. And once you have those two, you can change them simultaneously if you like, by doing it in 2 steps, since we know that this is an equivalence relation. Okay, so basically we've taken the category of topological spaces, and what we've done is we've identified a lot of continuous maps together. Okay, so the notion I want to talk about here is that of homotopy equivalence and contractible spaces. Okay, so we have a new category, homotopy, and a homotopy equivalence is now just an isomorphism in this homotopy category. And the point is now that in this new category, a lot more things will become isomorphic. Basically because to be an isomorphism, what you need? Well, you need inverse maps which equal the identity. And here to equal to the identity, it's easier to equal to the identity because the identity is now a whole equivalence class, homotopy equivalence class of maps. Okay, so that's the first point. Okay, so unfortunately, it may be very difficult to classify things up to homeomorphism, but if you want to try to classify things up to homotopy, that still tells you a lot of information. Okay, and remember, it certainly also means that if things are not homotopy equivalent, they're not homeomorphic. Okay, and it turns out to be an easier problem and something that you might be able to approach using algebraic techniques. Okay, so I guess the most important thing is to look at the trivial case. Okay, and The trivial case is not as trivial as for topological spaces. So there are two trivial topological spaces. Okay, the unique, the initial, the terminal object that you have here is a point. Okay, so the contractible spaces are those which are homotopy equivalent to a point. Okay, so so let's just do an example of showing something that is a contractible space, so you can see firstly how this notion of being a homotopic equivalence is a lot weaker than homeomorphism. Okay, and then you'll also see in this example how the notion of homeomorphism does imply homotopy equivalence. So if things aren't homotopy equivalent, we know for sure that they're not homeomorphic. Okay, so I claim that if you look at this rectangle, this solid rectangle, which is the interval -1 to 1 cross -1 to 1, this is contractible. Okay, so let's see what that means. So remember, you're talking about isomorphisms in a category. Okay, so what we need is to be contractible, this has to be isomorphic in this homotopic category to a point. So we need inverse maps, pi and iota, between x and the point. So say pi goes from x to a point. Okay, that has to be a continuous map, and there's only one unique map. So remember, point is the terminal object in this category. Okay, and we need to pick a map from the point to x. And actually, anyone will do. But to write the proof nicer, I'm going to pick one that allows you to write down the homotopy very easily. So I'm just going to send this map point to 0, 0. Okay. So that's the one we'll make writing of this proof very easy. So these are maps inside continuous maps, so they're inside the topological category, and I claim that they will give you inverses inside the homotopic category. So we want to basically say that this here is equal to the inverse of iota. That's what you want to check. Okay, that equivalence class of this iota. So this is invertible, and that they're inverses of each other. Okay, so basically what does that mean? It means that when you compose them, and remember the composition is just a homotopy equivalence class of the composition of pi and iota. Okay, and you want to say that that's the identity, so it means it's homotopic to the identity. So let's look at iota first, and then you do the pi. So if you do iota, you map the point to x, and that x, all of the points, including 0, 0, get mapped to the point. So that's just the identity on the point. So really here, it's clear that the composite of the equivalence class of pi with the equivalence class of iota is the equivalence class of the identity. That's pretty easy to see. Okay, so let's look at the other order when you do the equivalence class of iota composed with the equivalence class of pi. So you look at this here. If you think about what this map does, what does this map? So you do pi first, which is x, this whole rectangle, or this square rather, gets mapped down to a single point, and then you put this point into 0. So it's basically mapping everything down to 0 like that. Okay, and that's clearly not the identity, but to say that the equivalence class of this equals the equivalence of class of that, so they're same in homotopic category, just means they're homotopic. And so what I need to do now is to give you a homotopy from one to the other. Okay, so the homotopy I'm going to give you is going to map, so remember this is a map, these two are maps from x to x. The first one is the identity on x, the other one is the map from x down to this point here. Okay, so we need a continuous map from x across the unit time interval to x. And all that I need to do here is to map xt to, what I'll do is given any point like this, I'm just going to scale it by a factor of t, which is between 0 and 1. Now at times t equals 0, every point gets shrunk to 0. At time t equals 1, okay, you just multiply them by 1, so you just get x maps to x, that's the identity. And in between you scale up to t. So basically, if you want to think of this as some sort of animation, you at time t equals 1 and run backwards, it's just the identity. And then in time, when you go backwards in time, it just shrinks it down to the point 0. So that shows you that this gives you inverse morphisms in the homotopy category, and hence this gives you this equivalence class and this equivalence class here. They're isomorphisms in the homotopic category, and they're homotopy equivalences. So these this space X is contractable, and I hope you can kind of see from this particular example why we use the word contractable. I mean, we're kind of squashing things down. If you note this proof, okay, this proof is quite robust. You can use it in lots of different examples, okay. So if we place this square with a circle, okay, and in fact anything, as long as given any point and you multiply by any scalar, okay, it stays within the set, then you're okay. So such subsets of Rn are called star-shaped, and you can always shrink them down onto the center of the star, so to speak. So when you're in that case, then you will get a contractable space. I hope you enjoyed this adventure in pure mathematics.